Hello, everyone. This is Professor Burns. I'm here to present to you Lecture 5. Thank you all for joining us today. So let me go ahead and share my screen just so you guys have all of the information. All right, so we'll be looking at a few things today, all surrounding how to convert numbers. As you guys already know, you did have that as part of your second programming assignment. So we're going to look at how we do that and basically go into why we do that in the first place. So we'll talk about number data types, floating point specifically, and then the IEEE 754 floating point number standard. Now, as we look at numbers overall, we know that C and other languages have different ways of representing numbers, right? Or really different data types, right? We can look at a character, whether it's signed or unsigned, integers, your short numbers, your long numbers. And when we look at floating point, they provide more accuracy than what an integer would. And they allow us to describe the number in a little bit more detail. But as we know, as we've talked about in the previous lectures, floating point numbers are not just immediately recognized by the compiler, right? Your compiler, I'm sorry, by the CPU. That's only going to recognize things. Your machine's only going to recognize things in terms of ones and zeros. So the question is then, how do we take these floating point number and put it in a format that the computer can recognize, since it's only looking at things in terms of ones and zeros? And also this kind of shows the table of some of the amount of space each of this information takes up, right? We see these integers are going to end up, I'm sorry, the long numbers are going to take up more space, of course, and it tells you kind of the precision and the largest number that you can hold in a particular item. Now, floating points are going to give you more accuracy and more precision for your number, but there has to be a standard way to represent them in binary, just so that it's easier for your CPUs to process them. So step in with, okay, I want a standard way to represent that. How do I do that? Well, we figure out a way to do that, and then we create something that can be used universally. Hence the IEEE 754 standard representation. What it does is it takes your floating point value and it converts it to this binary form. It's good because it allows a standardized format, and as I said before, it's easy to be interpreted by the computer. So the one of the most common formats is this 32-bit format, which is called a single point floating point representation, where it's represented by 32 bits. 32 bits, also known as 8 bytes. And each of those, actually, for all of the 754 breakdowns for the representation, they all have these 3 sections. Something that's called the sign, right? And that's 1 bit of information. And what that does is it's going to indicate whether our number is positive or negative. It's just that 1 bit. That's the easiest thing to determine when you're looking at the number. Is it positive? If it is, it's going to be 0 for that first bit. If it's negative, it's going to be 1. The exponent, now this can vary depending on the type of 754 format that you want to implement. But for this one, we're looking at the 32-bit version. It is done, the exponent is 8 bits, meaning that you have 8 bits to store your information in. And we'll talk about the relevance of that because it will determine how big or how small your number can be. Now, this 8 bits, or the exponent, is really the size of the number kind of before the decimal point, right? How big is my number that I'm putting in there? So the whole part of the number. Now, it can be, represented in terms of positive and negative, and it can be used for large or small values. Now, the important thing about this exponent is that it is biased, which means that it's going to be weighted depending on what we are using as the base. And we'll talk a little bit more about that as we go into how to solve for these particular items. And finally, one of the other things that we want to talk about is, sorry about that. So we have this third portion, which is the mantissa. Now, the mantissa deals with the fractional portion of the floating point number. And for the 32-bit format, it is 23 bits long. So we have 1 bit that's for the sign, 8 bits that's for the exponent, and then 23-bit, which is dealing with the fractional portion of the number. Now, this is for a 32-bit version of this, but as we go on, you'll see that there's different versions of this format, like the 16-bit and also the 64-bit, which have the same breakdown, but the number of bits, except for the sign bit, which is also 1, the number of bits for these two are going to vary depending on the complete size of space that's allotted for the number that you're representing. So let's go a little bit into this 32-bit representation for single precision floating point numbers. So let's look at this example. Let's say we have this number that is minus 53.125. How do we represent that in binary? This this shows our space of 32 bits that we will be allowed to input our data, right? And here's the breakdown of each bit. The first one, of course, we already talked about, that's a sign. Is this positive or negative? The second one is the exponent portion, and we'll go into how to calculate that. And then the third one is the mantissa, which is the 32 bits remaining after we have the exponent. So let's get started. The first thing is the easiest bit to find, right, is the sign. For this one, it's negative 53. So our sign is going to be negative, but that means this bit is 1. For the next one, let's talk about how to calculate the exponent. Now, calculating the exponent involves a few different steps. The first thing you need to do is convert the whole number to binary. Now, our number, right, without any sign, without any fractional points, is 53. So that, when we convert it to binary, right, if we look at it in terms of bits, right, this is starting from bit where 2 is equal to 0, right? 0, 1, 2, 3, 4, 5, 6, 7, right? If we look at it in terms of that, we know that if I add 32, 16, and 4, excuse me, 20, this will give me 52. And then if I add another digit here, I'll get my 53, right? So this gives us our binary representation. This is how it would look in binary. It's going to be 110101, right? That's our binary representation of just the whole number. So that's the first thing you do, get the binary representation of that whole number. The next thing you want to do is convert your fraction to binary. So step 1, convert the whole number to binary. Step 2 is to convert the fraction to binary. Now this process is a little bit more, it's a little different. So our fraction for this portion is 0.125. So the first thing we would do is we're going to multiply this number by 2 until we get 0 in front of the decimal. So let's look at kind of how that looks, right? If I start off with 0.125, I multiply it by 2, right? Then I'm going to get 0.250. If I multiply that by 2, right? You keep on doing this iteratively until you get all zeros. Until you do that basically, and you stop when you have 0 in front of that decimal point. That means you have determined the binary version of what this exponent is represented as, right? So the first time is, if you see, this is my first column, I take that initial number, multiply it by 2, I get 250. I then take 250, and then I multiply that by 2, I get 500. Then I take 500, I multiply that by 2, and I get 1. So now I have 1 here, and at the right of my decimal point, I have a 0, so that means I can stop. Now, these numbers that are highlighted in red, right, where I have the 001, that is my binary representation of the exponent for this number. So now I've just done two things, right? The first thing we did was convert. Now, this is just for the exponent itself. This is not the full number. This is just the exponent that I'm using for this particular information. So now I have that first portion is my binary or the whole number, right? 110 or 00110001. And then to the right of my decimal point, I have 0.001 or 001, right? That's a combination of the two representations of those together. Now, my next step is I want to go ahead and put this in scientific notation. Now, you guys remember scientific notation from grade school, right? If I want to represent something to the power of 10, if I want to say, hey, I don't want to have 462, I want to with a single digit, all you do is you pull that digit back, you move the decimal point, and then you multiply it by whatever your base is in order to get the number that you want. Typically, it's 10, right? If I have 462, I can also represent that by 4.62 times 10 to the 2, right? It's the same thing, that same principle here. What we're going to do is we're going to take this and we want to move this decimal point over until we get to this first one, until we get to wherever we find the first number, that first one in our digit, right? So I started here and I moved this over 4 places. So the 4 places is what I moved over. This number is going to be very important because it represents, just like if I said, if I had 462, 4.62 times 10 to the 2, those 2 decimal places would be the exponent that I'm using in order to get back to the original number. All right, so then what happens is our base number, right? When we're dealing with scientific notation in our regular form, the base is 10. For this, we're dealing with binary. That means that our base is 2. So we have this number, 1.100100001 to the base of 2, right? To the 4th power, right? Because I moved my decimal place 4 points back, right? Since I'm moving it to the left, that means my the exponent attached to this, then it's going to be positive, and that is how I get my particular number for this guy, right? So now I have this number. Now this is going to be extremely important because this helps us to get to the next portion of our conversion. So keep in mind, this is all just to do our exponent, right? We already talked about the sign. Now we're on our exponent. So this leads us to a value where now that I know what this binary representation and I have it in scientific notation, now I can go on and determine the rest of what my exponent is supposed to be in this new format. All right, so here I'm starting with this number. I want to determine my precision exponent, right? And what does that mean? It means that looking at this, how precise can my number be, right? So keep in mind that when we talked about the number of bits that are being represented here, right? I'm going to go back several slides. We have 8 bits that are representing the exponent, right? 8 is our number. We have 8 bits representing the exponent. This will help us determine what our precision value is. We have 8 bits representing the exponent, and I can use that to determine how precise my number is going to be, right? If I consider n as the number of bits used to represent the exponent, I can determine how many things I can fit into that exponent value by using this equation here, 2 to the n minus 1, that whole thing, and subtract 1 from that. That will give me my numbers. That means I can fit up to, this amount of information in there, which ends up being 127. So 127 becomes my precision exponent, or what I'm using to calculate the data, right? Now I'm going to take this exponent, and then I'm going to use that. So now this is all dealing with the exponent. Keep in mind that this is all now in binary. This is all in bits. I want to calculate my bias, right? So I already know I can fit 127 bits here. This is, or I could fit 127, I shouldn't say bits, I should say values into this particular item. But I also know there's something involved with how I have moved this decimal point around and how the number itself is represented, because now this is not in the original format, but I moved this 4 spaces. So I also need to include that information in terms of my bias. So your bias for this, for the exponent, is always going to equal your precision exponent and your fraction exponent. My fraction exponent means I'm doing this 2 to the power of 4. That's my fraction exponent. And when I look at that, my bias for this, the bias for this particular number is 131. And that is just a combination of both of those put together, right? 4 represents how many times I had to move that decimal place over to get this to the leftmost point of my number. And 127 is by default that space that is allowed. It's how precise I can be, given that I am allowed 8 bits of information to store the exponent. All right, so 131. Now that I have that number, it is 131. That's what I'm dealing with. I can go ahead and convert this to binary to get my exponent representation. 131 in binary, same format, right? It's basically going to be this number here, because I know if I add 128 and these two here, I will get 131. So the binary representation is 1 0 0 0 0 0 1 1. All right, so we have just gone through and calculated or determined the binary representation of our exponent, right? Our 8-bit exponent. The first thing we did was we converted this whole number to binary, then we converted the fraction to binary, then we use that to get the bias that we're using to represent this, right? Because it's 2 to the power of something, right? Once we had the bias, then we went ahead and converted that to this number that we have here to represent our exponent for this particular number. Now, this next portion is where we're going to get the mantissa. Now, the mantissa refers to, or the mantissa, excuse me, refers to the fractional portion of this particular number. So remember when we had that that number that I had before, I said it's going to be really important. When we move this decimal point back all these spaces, this right here, after the decimal point, right? Once we get to that leftmost portion of the mantissa, this decimal point here where it is, after it, that is your mantissa. That's what's going to be your fractional portion of this binary representation. And anything that's left over, because remember, I have 23 bits and this one is only 7 bits long. Anything that's left over, you just fill it with zeros. So then we have our number here, 1 0 0 1 0 0 1. And everything else that we're left over with, it ends up being all zeros. And that is it. That's how we calculate and get this binary representation for 32 bits. Now, those steps in this process is the same thing. It follows that the same thing is true as we go into, this is 32-bit, but I can use the same process, and we will, for the 16-bit representation. Now, the 16-bit representation for the IEEE standard is sometimes called half precision, right? But it uses the same format. The only thing that changes here then is the number of bits that's associated with those two values. So let's go ahead and look at an example. If I had minus 28.1, how would I represent that? Well, the first bit is always a sign bit, right? That's going to be 1 bit. When I look at the exponent for this particular one, I'm only going to have 5 bits that are associated with the exponent. And when I look at the mantissa, I'm going to have 10 bits as opposed to 23, right? So my size of this has gone down, it's decreased, which means it's got to be a little bit less precise, but I can still use it to represent the number. So let's go ahead and get to it. Let's start with the exponent. The first thing I'm going to do is going to convert the whole number to binary. I have 28. And yes, you have guessed it. this is how we convert that to binary. It's going to be 1, 1, 1, 0, 0, 0, because we already know that when we add these all up, if we're looking at this in binary, right, 2 to the 2, 2 to the 3, and 2 to the 4, added together will give us our 128. So then our binary representation of this is 1, 1, 1, 0, 0. All right, now for this one, this fraction is a little bit more tricky because we don't get a nice even number of zeros for this. So we'll talk a little bit about that. Instead of us just getting, okay, this is eventually going to get to 0, it ends up repeating. But the principle of what we're doing is still the same. We want to convert our fraction to binary. And the way we're going to do that is we're just going to keep on multiplying by 2 until we get 0 in front of the number or until the number repeats. All right, so this is what it looks like, right? First number I have is 100. I multiply that, I get 200. Multiply that, I get 400. Multiply that, I get 800. Now, here's what's important to note here. And the only thing we're concerned about is this point after the decimal, right? So when I multiply this and I get 800, 8 times 2 is going to give me 16, 1.6, right? But when I bring this over here, I don't care about the 1. All I'm going to multiply is just the decimal portion of this, right? So this converts to, instead of being 1600 over here, it's just going to be 600. Similarly, when I have 1200 over here, it doesn't, I'm not going to go back and just have this at 12, but I'm going to keep this listed. I'm going to keep this at 2. So I'm going to keep this at 2, which means that I'm bringing my 2 over here. And then once I do that, I end up with 400. Now, notice how we didn't get to 0 yet, but I have the same number that I have up here, which means what's going to happen is this fraction is going to repeat itself. It's going to keep on going, and you're going to get the same thing over and over and over. So let's go ahead and look at what this looks like in binary format. Well, it looks like this, right? 0, that's we're at, but that's the first number. So it's 3 0 0 0 0 1 1. Those are my two numbers here. And then what you'll notice is that after that, it starts repeating. Oh, really? You know what? It started repeating here. So it actually is repeating at the 2. Because we see that 2 already come up here, and that is where we kind of say, okay, this is the same number over and over. Let's go ahead and make that correction real quick. All right. All right. And not the whole number, just this 2 portion here is where it repeats. Oh, you know what? No. I was correct the first time. You know why I was correct? Because so where this actually repeats, because this is at 200, but this is actually looking at kind of the other number, this is kind of the representation for how it repeats. All right, so we repeat this, we get the number there. So let's go ahead and look at how that looks and the space that we're going to move this back to. When we move this number back, we're actually going to do is, again, we're going to get it to the first one that we see. So we're going to move this over 1, 2, 3, 4 spaces again to get this as our mantissa. So then the mantissa ends up being this number that we have here, 1.11000000. This is not confusing at all. 11000011 times 2 to the 4. And 4, again, is our exponents, right? That is going to help us get our bias. So let's go ahead and get that. Now we want to determine the precision. Now, before we were dealing with 32 bits, So we have 8 bits for the representation. This time, we only have 5 bits. So when we deal with our precision exponent, instead of us having 2 to the 8 minus 1, we have 2 to the 5 minus 1, which ends up being 2 to the 4 minus 1, or 16. And we subtract 1 from that. That means we have 15 bits to deal with in terms of precision. And we know that, or 15 places, I would say. And we know that n is a number of bits assigned to the exponent, which in this case is 4. Right? So 15 is a number that we're using to help determine our bias. And as we said before, it's the same equation. We're going to use the precision exponent, add that to the fraction exponent, and that will give us what our number is for the exponent, right? Precision exponent, 15, we just calculated that. 4 was from this before, when we converted both the fraction and the whole number to this binary format, and we end up with 19. So now I take 19 and I convert that to binary, and that gives us 1.0011. So now I know what my exponent is in 5 bits. It is 1.0011. So now I have 2 portions of it. Now let's go ahead and wrap this up and finish this out with our mantissa. For the mantissa bit ends up being what we have calculated previously during our evaluation, right? It's this 110000000110, right? And then if we had a 32-bit, it will continue repeating out, but we don't. We just have these 16 left here. So this is then our number and our conversion for that particular item. All right, so hopefully that makes sense. We're gonna do one more. And this is one of the ones you had for your homework assignment, right? You were asked to do the 16-bit conversion and also the 8-bit conversion. Now, when we look at an 8-bit conversion, what happens is that, the representation is not really technically an official IEEE standard, but more and more people are kind of using it. And for the 8 bits, what we have is 1 bit being for sign. That's usually going to be the case. 3 bits for the exponent, which means you're going to be dealing with an extremely small number, extremely small. Right, between -7.5 and 7.5. And then the mantissa is 4 bits long, right? Just because that's the only number of bits you have available. But the process is still the same. We convert the whole number to binary, super simple, right? That's going to be 111. That represents 7. We're going to convert the fraction to binary. And we're going to keep on multiplying until we get to 0 or until the number repeats. And so we multiply this. Thankfully, we only do this twice. 250 times 2 is 500, and then 500 times 2 gives us our value that we want. So we end up with something being very simple for this. It's just 0.01. And when we combine the things, we're left with a very simple number here for our binary conversion. And of course, we still need to move this decimal place over 2 spots so that we can get the scientific notation representation of this number. And then 2 becomes our exponent that we're going to use. Now, the precision for this is, again, our n, right, is 3. So it's 3 minus 1, which gives us 2. 2 to the power of 2 is 4. 4 minus 1 is 3. So our precision exponent is 4. And we can use that to then determine our bias. I'm sorry. It's 4 minus 1, so that's 3. We didn't use that to determine our bias. So 3 plus the 2 we've already calculated up here as our fraction becomes the number that we use for our bias, and that's 5. 5, when we convert it to binary representation, is 101, right? Those are the 3 bits that go into our exponent format. So now we have everything that we need to go ahead and write this to a 8-bit representation. The sign of the bit is 0, right? Because this is positive, so that's going to be 0. My exponent, I already said that, is the representation of representation of 5, which should be 1, 0, 1. Oops. All right, so that's 1, 0, 1. And then our mantissa bits, those are what we already calculated here. It's going to be 1, 1, 0, 1. And that's it. That's the 8-bit representation of this particular number. All right, there's one more item that I want us to go over, and that is how we do this, how we handle fractions, right? We talked about how that exponent, we talked about how the fraction could be positive or negative. So let's take a look at kind of how what that looks like. Imagine I have a number, this number right here, right? It's just 250. 16-bit representation. So we're still gonna have 1 for sign, 5 bits for exponent, mantissa is 10 bits, blah, blah, blah. We know that already. First thing we want to do is convert the whole number to binary. Well, there is no whole number, it's 0. So that means when we convert it binary, it's just going to be all zeros, right? Then we convert our fraction to binary. Now, the fraction we've already done in the previous example for 25 or 0.25, you end up having a 0 and a 1, right? So this ends up being 0.01. Now, if we combine these, notice how we have this, right? There is no 1 to the left of the decimal point. So what do? Instead of moving the decimal point to the left, we're going to actually move it to the right. We move it to the right, which means when we look at our exponent to the base of 2, it's going to be negative instead of positive. That's what you see right here, because I moved it in this direction. And that shouldn't be 4 spaces. It should actually be 2 spaces. Let's go ahead and update that. All right, so we moved it 2 spaces to the right. All right, now let's do a calculate the bias, right? 1, we moved it 2 places to the right. So when we do our calculation, right, the precision exponent we know already from the previous slide that it's 15 digits of precision. And we're looking at a value of that, and we're going to add the fraction exponent, which ends up being -2. So it's 15 minus 2, that gives us 13. Notice how it's not a positive number, but it's the minus number. If we convert 13 to binary, we get 0, 1, 1, 0, 0, 1. I'm sorry, 0, 1, 1, 0, 1. That's our binary conversion of 15. All right, so then let's go ahead and do this conversion. Very simple. The sign is going to be 0 because it's a positive number. We already know that 13 gives us that in terms of our binary representation. And the mantissa, it just happens to be 0. There's nothing there, right? But that is how we would work. Wow. Not do that. Sorry, I carried over from another slide. It should be. And this, when we look at it, when it's carried over, that is what gives us our number, 1.00 times 2 to the -2. So our mantissa happens to be all zeros for this. But the important thing to know is that because there's, it's only a fraction point, we have to move this decimal point to the left. I mean, we have to move the decimal point to the right when we do our scientific notation. So that ends up giving us, that's why we subtract it from that item here. And that's how you work with fractions. This is 0.250 as a fraction. And that will end our lecture for today. Thank you all for joining us or for joining me for this lecture. I will see you again. Feel free to reach out to me if you have questions. I did post the date for the midterm. We've switched it to next Tuesday, so make sure you get ready for that. This will be on the midterm, so do take a look at it and understand. Make sure that you're familiar with conversions. All right, guys, until next time.